Picture a photograph of a dense forest. Now, imagine a camera that just keeps zooming in on a single leaf. Eventually, the smooth, natural edges disappear, and the image breaks down into a harsh, blocky grid. This happens because computers have a hard limit. They cannot process the true, continuous infinity of the real world, so they chop it up into tiny, finite pieces called pixels to make it manageable. Mathematicians run into this exact same limit when they study something called groups. Think of a group as a mathematical rulebook describing the symmetries of an object, like the specific ways you can shuffle a deck of cards or rotate a crystal. Many of these rulebooks describe infinite objects, which are too massive to study directly. To handle them, mathematicians try to pixelate the structure, breaking it down into smaller, finite systems that they can test and verify on a computer. Just as a screen needs a finite number of pixels to display a forest, mathematicians rely on these finite approximations to make sense of infinite complexity. When a mathematical structure can be successfully and perfectly pixelated this way, it is called a Sofic group. For decades, almost every symmetry system mathematicians worked with turned out to be Sofic. It seemed like every infinite structure in the universe followed this rule. But in 1999, the mathematician Mikhail Gromov raised a challenge. He asked if there was a limit to this. Is every infinite structure in the universe actually pixelatable? For 27 years, no one could find an answer. Mathematicians couldn't prove the rule applied to everything, but they also couldn't find a single NonSofiic exception that broke it. To prove Gromov wrong, someone must find a mathematical object so rigid that it shatters any attempt to model it with finite pieces. In late 2026, an OpenAI model bypassed the decades of theoretical stalemate by constructing a physical blueprint for this impossible, unpixelatable object. The AI built this object using two conflicting ingredients. First, a mathematical structure with rigidity, its internal connections tightly locked. Second, Thomson's group V, which is infinitely flexible. The AI glued them together, forcing these incompatible behaviors to share a central point. Attempting to drop a finite pixel grid over this shape breaks the math. The rigid half forces the flexible half to stop, making the structure impossible to approximate. Because this object literally shatters when forced into finite pieces, it is a proven NonSofiic group. The breakthrough wasn't just an abstract idea. The AI provided what is called a finite presentation. This is a step-by-step instruction manual to build the shape using a finite list of starting pieces and the specific rules for how they fit together. This manual allowed human mathematicians to check the machine's work. They could follow the instructions themselves to confirm that the object really does exist. The AI handed humanity a verifiable blueprint for an object that had been invisible to researchers for nearly 30 years. This discovery changes how we look at dynamical systems, the mathematical tools we use to track how complex things change over time. To predict how a massive storm evolves or a planet orbits, we simplify the system into finite, pixel-like chunks a computer can handle. For decades, these models have worked because scientists assumed every system's underlying symmetries could be simplified this way. But we now know that some systems are non-Sofic. They have internal rules that cannot be pixelated. If a weather pattern or a physical system follows those rules, our current models have a blind spot. They are using tools that literally cannot see the full picture. This AI result is forcing us to rethink the math we use to describe reality, moving beyond the tools humans were able to find on their own. The map of mathematics has just grown larger, revealing a hidden layer of complexity that will require us to invent entirely new ways of understanding the world.